So today we're going to do the supersonic nozzle. And this is a pretty fun experiment. What we got here is we've got a few nozzles. This is an example of one of them. Each nozzle, along the nozzle, there's taps, little small pressure taps, and you can see they're numbered here. And it's basically just a straight hole to the interior of the nozzle. Each one of these taps is connected to a tube, and this tube is then connected to one of these pressure gauges. So we have 1, 2, 3, 4, 5, 6, 7, 8 gauges along the length of the nozzle. What we can do is we can create a pressure difference across the nozzle, and we can adjust the flow rate to set up different flow fields through the nozzle. All right, so let me pressurize the front end of this. So we're running this off of building air. So we're about 900 kilopascals here on this gauge. Same on the backside because we have no flow. So we basically just have static pressure running through the gauge. When I open this, this will allow flow to come through the nozzle. We're going to measure the fore and aft pressure, the temperature difference across the nozzle, the pressure profile through the nozzle, and the flow rate. So now that I know what the pressure profile is experimentally, I can compare this directly to the analytic solution that we derived in class, the isentropic flow through the nozzle. We can also see where the standing shock is. So let's try that out. So let's have a look at some of the data. Here I'm showing you the nozzle profile, and I just want to point out a few things before we get started. The throat is located here at location 2. It's 1.5 millimeters from the leading edge of the nozzle with a diameter of 2 millimeters. So a diameter of 2 millimeters means the area is 2 divided by 2, radius squared is 1 times pi, so it's 3.14 millimeters squared. And the reference pressure that I'm going to use through most of my calculations is located here at this position 8. And it has a diameter of 2.79 and is located 6 millimeters downstream. All right, so here's a typical pressure profile. The stagnation pressure for this data was collected when the upstream stagnation conditions were 851 kPa. And you can see that if I calculate this magic number here, this critical pressure ratio, 0.5283, it works out to about right here, about 450-ish kPa. So you can see this particular profile, I'm expecting to be along the supersonic branch for a while and then maybe jump to, through shock conditions to a new isentropic branch. The back pressure here, or the exit pressure, was 471 kPa. If I increase the exit pressure to 800 kPa, you can see I'm nowhere near this critical pressure to choke the throat, and I probably am on the subsonic branch all the way through the nozzle. I think I'm going to work mostly in dimensionless form, so I'm going to divide all of the data by the stagnation pressure, resulting in pressure ratios from 0 to 1. Here's all of the data I collected for a variety of exit pressure ratios, going from 0.959 to 0.096. And you can see here that even though I've connected these with straight lines, maybe I shouldn't have, right? Because one of the isentropic solutions comes down to here maybe. You can see that the only way to get up to that branch, to deviate from the isentropic solution, is maybe to jump up with a shock and then follow it on out. So keep that in mind moving forward. All right, let's review the theoretical solutions we have at our disposal. The first is the isentropic relations. So we have the equations in terms of Mach number here that describe the change in pressure and temperature and density through the nozzle. And graphically, it looks something like this. Recall what this is. This is our two solutions, our subsonic and supersonic branch, and then we can read off what the temperature, pressure, density ratios are, respectively. The Rankine-Hugoniot equations look something like this. You have a standing shock in the nozzle with the reference 1 subscript in front and 2 in the aft, and based on the upstream Mach number, you can calculate the pressure or temperature or density jump across the shock, the downstream Mach number, and the change in the reference area. All right, so with these guys, we are able to then calculate some theoretical solutions through the nozzle. So if I have a back pressure of 851 kPa, I'm not going to get any flow at all, right? So that's kind of our trivial solution. If I lower the back pressure just a bit to 840 kPa, so I've got a pressure ratio of 0.987 on the back of this nozzle, I expect to get some flow. And in order to calculate this isentropic solution, let me show you how I did it. The first thing we're going to need is this A star, right? And so the way we're going to get A star is we're going to solve for the local Mach number. I'm going to use 840, that's this pressure back here, along with the stagnation pressure to create a pressure ratio. So I can solve then what's the local Mach number at this 6 millimeter station. That's right there. So knowing that Mach number then, I can calculate what the area ratio is. A over A star is equal to this Mach number relationship. Well, I know Mach number and I know the area at this location, so then I can calculate this A star. You can see here that it's less than that 3.14 millimeters squared number. So that's the area I would have to neck this throat down in order to just choke it, right? So the real area is larger than this area, so I expect it will remain subsonic all the way through, and we get something that looks like this solution here. You can calculate it by just solving for the various area ratios. So you just take the area at the throat and divide it by 1.44. Take the area at the exit, you get this. And likewise, these areas are all known because we know the nozzle geometry, and you can calculate these values here. And then from the graphical solution, you could calculate the Mach number along the subsonic branch, and then the pressure ratios along the subsonic branch. So graphically, it looks something like this. We came down that branch, the subsonic branch, till we hit the throat. The throat is sitting there at an area ratio of 2.17. That's right there. Mach number of 0.279 and a pressure ratio of 0.947. So you can see that's where we get this number right there, the pressure ratio. And then because we're nowhere near choking the throat, we just return along that subsonic branch as we move through the nozzle. All right, we can continue on in this way and calculate all the theoretical solutions along the subsonic branch while we continue to lower the back pressure. Now we get to this point right here, and things start to get interesting. This is right at 794. This is at an area or a pressure ratio of 0.933. There's nothing special about that number, but what is special is we're just touching that critical area pressure ratio 0.5283. So right here we know we're just choking the throat, right? And so we're going to return along the subsonic branch. And if I pull it a little bit lower than this 794, we're going to move along the supersonic branch. So just to remind you again graphically what this looks like is, at this back pressure, we've just pulled the nozzle all the way to the critical conditions, or Mach number equals to 1. And then depending on what the exit conditions are, we could follow the supersonic solution right on out, or we could follow the subsonic solution back along that same branch. So in order to just pull it all the way along the supersonic branch, we can plot what that would be. This is the supersonic solution, and I would need a back pressure or a pressure at the exit of 83.9 kPa. So that's quite a bit lower than this 794.5. That's pretty cool, but the question is, what happens for any pressure between these two, right? What happens if I set the exit pressure somewhere in there? Well, the answer is we're going to get a shock wave, right? So let's see. Imagine that I'm set my back pressure to somewhere about here. I'll set my exit pressure to somewhere about there. And so what we're going to have to do is follow along with this burnt orange solution here. This is our isentropic solution through the nozzle. And in order to hit that boundary condition or that exit pressure, we're going to have to jump up along some shock and then follow the isentropic solution on out from there. So that means that to get this isentropic solution, I'm going to need some new area ratio. And this corresponds to a new stagnation pressure as well, right? In order to get this shock jump, I can use the shock jump relationship. So I have an isentropic branch, I have a shock, and then I have a second isentropic branch. And so you could do this for any back pressure. So if you had a back pressure of 260 at the exit, then you might follow along the isentropic solution till you got to about here, let's say. You would jump up and then follow that isentropic solution on out. So that's the basic idea of how we get through the nozzle. Let's compare then the data that we collected on the experiment to the analytic solution. So here's one here. Here I set the back pressure to 816, and I calculated what the isentropic solution should be through the nozzle. We're nowhere near the magic number of 0.52, so I suspect that this is just along the subsonic branch and returning along the subsonic branch. In order to calculate this isentropic solution, I needed to know what the critical area is, 2.51, which is much lower than the current nozzle area. Here's the corresponding experimental data. Now, I match this isentropic solution to this exit pressure, so of course the isentropic solution hits the experimental data exactly. But you can see that it deviates, especially in this throat region. So the throat isn't going to a low enough pressure, which means the velocity is too high, right? So it makes me think that maybe there's some frictional effects in the experiment that aren't accounted for in the isentropic solution. Here's another example where I lowered it, the back pressure to 800 kPa, and you recall from earlier, we're getting really close to choking the throat here, and you can see that we're even worse. The isentropic solution and the data are really quite far apart in the throat area, and of course they're right on each other at the exit where we match the isentropic solution. So here is that critical condition where at 974, I'm just theoretically choking the nozzle, and if I look in an experimental profile at 686, you can see I haven't yet quite pulled the experimental data to the critical throat area, but I am already in that shock regime. So the data just isn't following the theoretical solution like it should, the way you expect. Here's all of the data, and I plotted it along with the isentropic solutions just for reference. And again, just to point out that you can see that there should be shocks. Everything past this critical pressure ratio should generate a shock in the experiment. So let's now compare some of the data that we collected in the supersonic regime to the isentropic solution and the Rankine-Hugoniot equations. Here's an example profile right here. This is one where I was running the exit at 471 kPa. So you can see that we came on down, and somewhere here we must be generating a shock wave. Somewhere between maybe this location and this location. We have to have a shock and jump up. I don't know exactly where it is, but I know here I'm on the return isentrope, and here I'm still on the supersonic branch. So I'm assuming there's somewhere there's a shock. Now, if I wanted to calculate the isentrope along this part of the data, all I need is this critical area. So I can do exactly what I did before. I can use the pressure ratio and calculate that Mach number locally at the exit. So I know what that back pressure is because we recorded that back pressure in the experiment. And so that's the pressure at the exit is 471, and that back pressure is 501 kPa. So I have that ratio. Now I can calculate the local Mach number. And then using the local Mach number, I can calculate my critical area. So I get a critical area of 2.99. So that's the critical area associated with that branch. So now that I have that 2.99, I can compute the isentropic solution just like I did before. So I can divide everything by this 2.99. That'll put me on this guy right here. And then I can calculate the the subsonic solution, because once we jump, we're on the downstream side of the shock, we're on the subsonic branch again. And keep in mind that this is all relative to the post-jump condition. So that's a new local sound speed there and a new stagnation pressure. Also, because it's a new stagnation pressure, when we calculate the isentropic solution, we're really getting P over P naught 2, the downstream stagnation. So I need to divide by or multiply by the ratio of P naught 2 to P naught 1 in order to fairly plot the pressure ratios on this curve, which are all relative to the upstream stagnation pressure. So there it is there. That's the plot. And again, of course, we go right through the boundary condition. And then it looks like, I went ahead and plotted it to this location, so you can see the deviation there. But it looks like the shock should be in there somewhere. And this is a great story, except for it's a little bit of a problem. And that is that we got this branch by assuming that the isentropic solution has to go through the exit pressure, and that's true. But we could also ask to calculate then the Rankine-Hugoniot jump conditions anywhere between here and here. And if we do that, we see that we will not get a very good estimate of this branch here. And let me show you what I mean by that. So in this alternate approach, we could have, instead of matching the isentropic solution to the exit pressure, we could have said, well, I know what this solution is here. I know what the isentropic solution, if we followed this branch all the way to here, then I know what this Mach number should be. It should be 1.63 using the isentropic solution. And I could pick any value between here and here, let's say, and I could iterate on this later to see what effect it would have. But if I just chose this branch, so we're at this axial position of 3 millimeters, the isentropic solution tells me what the upstream Mach number is. I can then use the Rankine-Hugoniot conditions to jump using this Mach number of 1.63. So there's the relationship here. And so 1.63 squared, blah, blah, blah. And I can calculate what this downstream Mach number is, 0.659. If I use this, I can then calculate what the pressure jump is as well, right? So I know what this upstream condition is, 1.63. I can calculate the pressure to be 691 kPa. That's a pressure ratio of 0.718. So that would, if I use that jump condition, it would put me way above what the data is telling me, right? So the problem is, in this case, the solution is not supported by the data, the isentropic jump condition combination. I can carry on with this and calculate then what my new A star is on that second half, that post-shock, and I get a critical area of 3.55, and that critical area is bigger than the throat area, but it's smaller than this. It puts me about 3 millimeters, puts me about right here, right? It's smaller than that area there, as one would expect. So using that area, I could then recalculate an isentropic solution to move me back along this branch here. Of course, this isentropic solution isn't valid anywhere here because those area ratios are less than 1, right? Well, even this guy here. So there's a problem, right? I could say, well, what if I picked a different Mach number? What if I picked 2.3 as my Mach number? And that's not just happenstance. That happens to put me right on the branch. If I look, well, where does 2.3 occur in the isentropic solution? Unfortunately, if you go back and look, where's my isentropic solution? 2.3 is nowhere near, this nozzle doesn't have a Mach number of 2.3 in it. So it means then that really this condition is also not accurately reflected by the data. So we just can't win here. Finally, let's look at the mass flow rate through this nozzle. We experimentally measured the mass flow rate, and I'm plotting it here as a function of exit pressure versus, or divided by the stagnation pressure. Looks like it chokes about there, right? So that's not going to be the magic number because the magic number is pressure in the throat divided by stagnation pressure. But anyway, this pressure here says we've got these flow rates, and so it looks theoretically right? It starts off at 0 and rises, and then it asymptotes to the maximum flow rate. From the isentropic solution, I can calculate what the flow rate is given any local Mach number and local area. I can calculate what the mass flow rate is, and when I plot it on this plot, I get this blue line here. So you can see that isentropically, we should be having a lot more flow through this nozzle, a lot more mass moving through this nozzle than what we measured. So the experimentally measured choked mass flow rate, though, however, does match the isentropic solution. So that's pretty cool that at least we asymptote to the right solution once the throat is choked. All right, so in conclusion, the nozzle behaves generally as we would expect it to behave. I mean, you kind of follow along the isentropic solutions. On the subsonic branch, you return to the exit conditions, and then somewhere you begin to choke the throat, and you get these shocks. I mean, conceptually, it's all there. An isentropic solution will exceed this pressure ratio at some point. We get choked flow, and we match that flow rate through the nozzle, so that all makes sense. The purely subsonic flow rates are a little bit less than the mass flow rates, as we just saw, and that's maybe due to friction. The shock jump equations do not put us on the data, as we would expect, and the reason, I think, is because we don't really have good, clean, normal shocks. This is a couple of Schlieren images for a very similar sort of nozzle. Here it looks like you've got a nice normal shock, but here as we increase this back pressure and get stronger and stronger shocks, you can see there's some phenomena here that deviate from the 1D solution that we assumed. Like you've got these Mach stems forming. Those are multiple shocks near the wall. You can also see the boundary layer effects very, very near here. And keep in mind that we made our measurements using pressure taps. So those taps are very much influenced by whatever garbage is going on here with regard to the boundary layer. If we've got separation going on, it's effectively lowering or narrowing this nozzle, slowing, restricting the amount of flow we can get through there. So not a very 1D sort of shock. It would have been nicer maybe to have the sort of experimental setup where you can slide a hot wire in and make measurements that way. And in so doing, you get a much better representation of the one-dimensional flow. Finally, by knowing the back pressure, we could construct the isentropic solution which matches the exit conditions, and you get something that looks like this. That's not so bad, really. So we just compared the experimental result to the analytic solution. And we could see where the differences were. We could also see the standing shock in the data. This was for a steady flow. Next, we're going to look at an unsteady flow, a blowdown from a large tank. So we'll see you next time.